Hello everyone, this is an update from Dr. Nathan Forsyth. I am a University Research Fellow in the Water Resources Research Group within the Civil Engineering discipline in the School of Engineering at Newcastle University. I'm presenting on behalf of my colleagues Dr. David Pritchard and Professor Haley Fowler regarding working to avoid garbage in, which is our goal in terms of Newcastle University's contribution to the FutureDAMS project. So, I'm going to cover a number of points in this update today, giving a brief overview of our approach to the climate analyses work for FutureDAMS, explaining a little bit about the evaluations we've been doing of gridded data sets of historical climate in FutureDAMS case study geographic areas, focusing on the Volta Basin, also speaking about the design creation of basin-specific climate metrics to identify impact thresholds, again using the Volta Basin as an example, and also talking about providing some background on emission scenarios and simulations of future climate change, and then progressing to the planned methodology for producing targeted data sets for modeling and analyses of future climate change on FutureDAMS case study geographic areas. So, in terms of our approach to the climate analyses or analytical work for FutureDAMS, there's a truism that all models are wrong, but some are useful. This is attributed to statistician George Box and goes back several decades. To be more specific, of fully reproducing complex physical processes or representing human activities, but some are capable of having sufficient fidelity or accuracy, realism, in explaining the variability of system behaviors so that they do manage to provide meaningful insights that improve our understanding of critical phenomena and their potential impacts. So we here at Newcastle view our role in the FutureDAMS project to cover two primary points. First, we are contributing to characterizing the available historical climate data used as input for the various impact and framework models being developed throughout the consortium, so that the biases in those input data can be understood and accounted for, and thus hopefully mitigating at least the first component of the ubiquitous garbage in, garbage out modeling problem. Additionally, we will be working to synthesize a manageable portfolio of scenarios of projected future climate conditions data sets so that the impact and framework models can be used efficiently to evaluate across the broad range of potential outcomes within a large envelope of uncertainty. So, in terms of evaluating the potential gridded data sets that are being used as input to the framework models, thus far we've only been able to work on the Volta Basin because that is the basin which thus far we have been able to have access to local observations provided by Emmanuel Bovi's team at the CSIR WRI Institute in Accra. We've had access to data from over 24 stations, and a few more were presented but did not have sufficiently complete data to analyze. Today I'll just be focusing on results from a single station, but the reason that we use the gridded global data sets rather than the local observations themselves is the local observations themselves do not have sufficient spatial coverage to provide the detail necessary for the impact and framework modeling that is being conducted, and additionally they often have temporal gaps where there was a lack of observations for a range of reasons. So I'm showing example today of an evaluation of a station in Navrongo in northern Ghana. This is located in close proximity to an area that has been the focus of field-based collaborative research activities between the agriculture team at Manchester along with various partners in Ghana, including WRI and others, WASCAL in particular. So our approach to evaluating the representation or fidelity of the gridded data set with regards to local observations is we first focus on three key meteorological variables. We focus on precipitation. Rainfall is the obvious key metric defining or characterizing whether conditions are wet or dry. Then additionally we focus on daily mean temperature calculated as monthly means, and temperature logically characterizes whether conditions are warm or cold. And a third key variable that we use is what is referred to as the diurnal temperature range. It's the difference between the daily maximum and daily minimum temperature. And a large DTR tends to indicate that conditions are essentially clear or low humidity, and a low DTR would indicate that conditions are overcast and or high humidity. So in each of these evaluations we look at the variables in three aspects. First, we look in their absolute values, and those are what you see in the upper row of the figures presented on these slides. And so we're comparing the local observations, which are shown in black, the solid line for the historical period mean statistical values for each calendar month, January through December. And we're comparing them to gridded data sets. So we have ERA interim, JRA 55, NASA MERA 2, ERA 5, as well as two slight data correction nuances for the Princeton global data sets at a 25 kilometer or 0.5 spatial resolution. And what we can see for precipitation is that we kind of have two categories of data sets. One set that includes the Princeton global forcings and JRA 55, which match the, or essentially just Princeton global forcings, which match the observations relatively well. We also have the range of local observation historical variability shown in gray, and then for the gridded data sets, those are the dashed lines. And then the rest of the data sets tend to underestimate precipitation at Nivrongo in the absolute terms. For daily mean temperature, there is relatively minimal bias in any of the gridded data sets. It's relatively accurately presented in absolute terms. For diurnal temperature range, we do have two groups of data sets, essentially NASA MERA 2, the Princeton global forcings, and JRA 55, where the absolute values of DTR are relatively well captured, and then the others where they are underestimated. And actually JRA 55 is not in that group. But we also look at the data sets in terms of their relative performance. So we normalize the values rather than taking the absolute values so that we understand the distribution across the annual cycle. So for precipitation, what we do is we divide the calendar months by the annual total from that data set, and thus we see the relative distribution of precipitation across the annual cycle. And again, we see here that there is an improvement in the distribution of precipitation, although there are a set of data sets for precipitation that underestimate the ramp up of monsoonal precipitation in May and June principally, whereas other data sets capture it more accurately. The distribution of annual temperature is relatively well captured, although there is an indication that perhaps the end of the calendar year, October, November, December, is a bit too cool in NASA MERA 2. Diurnal temperature range normalization improves the degree of matching. So while some of the data sets may have underestimated diurnal temperature range, in the absolute terms, they tend to get the pattern of the amplitude of the annual cycle. And so for mean temperature and diurnal temperature range, rather than taking the fraction of annual totals, which is not relevant to temperature, what we do is we subtract the mean annual value for across the entire variable, and then divide by its range. The maximum month minuses the minimum month, and that gives us a relative amplitude centered on 0. And we see that the gridded data sets, despite any absolute biases, get the shape of the annual cycle of both those variables accurately. In addition, we also calculate the correlation between the anomalies in the time series of the local observations and the gridded data sets. And here we see for precipitation there is a clear clear winner, that the Princeton Global Dataset has better tracking across all months except with the exception of January, which would tend to be a very dry month and subject possibly to some minor outliers. Stronger correlation between the time series patterns of anomalies in shown by the Princeton Global Forcings with local observations in comparison with the reanalyses data sets from ERA Interim, ERA 5, JRA 55, and NASAM ERA 2. Performance across temperature is much more homogeneous, with the exception of NASAM ERA 2, which is slightly weaker in the latter half of the calendar year. And then in diurnal temperature range, results are a bit more mixed, but our overall interpretation of this for precipitation temperature, mean temperature, and diurnal temperature range is that the Princeton Global Forcings perform at least as well, if not better, and particularly for precipitation, than the reanalyses-based data sets. Additionally, what we look at for evaluating the gridded data sets is what we refer to as the climatic water balance. This is the supply and demand balance or equilibrium of atmospheric moisture near to the surface. So not within the soil, but just above the soil or ground vegetation. And so again, here we start with precipitation because that is the atmospheric input to the near surface of moisture. And then we also calculate what's referred to the reference evapotranspiration, or could also be called the potential evapotranspiration. Reference evapotranspiration is just a specific formulation based on a transferable standardized grass cover that can then be, the values derived can then be adapted using coefficients to represent a range of other vegetative covers or specific crops, usually because the method was developed for the Food and Agriculture Administration, the FAO, Food and Agriculture Organization of the United Nations. So we take precipitation as the input and reference evapotranspiration as the demand. So supply minus demand gives us the climatic water balance, abbreviated here CWB. And so periods where the climatic water balance is negative, that is times when the energy supply to the ground surface is such that the demand for moisture, the potential demand for moisture by the bare surface or by crops exceeds the amount of water being supplied. So attempting to grow crops in that period would be moisture limited, possibly non-viable, in the absence of the availability of supplemental water via irrigation. And so what we see in the annual cycles, the shape of the annual cycle of climatic water balance is dominated and matches or has a similar shape to the precipitation cycle, although there is some variability in the shape of the reference evapotranspiration. Reference evapotranspiration actually is at its annual minimum when precipitation is at its maximum. The annual minimum is caused in reference evapotranspiration because reductions in temperature and especially in incoming radiation due to cloud cover limit the amount of moisture which can be transpired through crops or evaporated from bare surfaces. And again, here we've already analyzed precipitation in terms of its relative variation and its correlations across time series of anomalies. Reference evapotranspiration behaves similarly to temperature and diurnal temperature range, which are proxies for the radiative or energy inputs which drive it. And then because the climatic water balance in this zone is dominated by the precipitation inputs, its relative performance normalized and its correlations are similar to those for precipitation. So this is an approach we can use to look and see which data sets perform best in across a range of metrics for representing the locally observed conditions within a case study. So our key takeaway messages from this exercise, and this is drawing upon the full range of stations which we evaluated far beyond the single station at Navrongo, so key takeaway messages are that we can have confidence that the Princeton Global Forcings datasets, which have been used in the historical hydrological modeling, which then is percolated out through the other impact modeling schemes, our Princeton Global Forcings are the most credible data sources available for driving the impact models for historical period. And in the Volta Basin, one of the spatial patterns we found, particularly for precipitation and diurnal temperature range, were that biases were influenced primarily by latitude. So we'd have different patterns of biases in the north, which was far removed from the sea and the Atlantic Ocean and source of moisture, compared to those that we would have closer, further south, but stations that were located on the same latitude had relatively similar patterns of biases. One of the things that we also have begun developing or exploring are the potential for defining various metrics of climate, which could be analyzed outside of modeling environments, modeling systems. And so one example would be a metric for calculating the onset in terms of which day of the year, starting from January 1st, the rainy season is defined to have occurred in the historical period. But this definition is subject to a choice of parameterization, including the amount of moisture that initiates the rainy season onset and the amount of time for which a certain minimum threshold of rainfall must not be fallen below. And so we have an example. We can range from a small or a lax definition at the bottom, where we only require 10 millimeters of rainfall, and not having a break of rainfall less than 5 millimeters in the subsequent 10 days. And that calculates a very early onset throughout the year. Or we could say of somewhat moderate thresholds, where we have to have 20 millimeters of rainfall to initiate the monsoon, and there must not be less than 5 millimeters a day, 5 millimeters per week in the subsequent 20 days. Or we could have a very strict threshold where we require 30 millimeters of rainfall to initiate the rainy season, and there must not be a break period with less than 5 millimeters per week in the subsequent 30 days or month. And so we can see for the very strict definition, that ends up with a much later identification of the day of onset. What we can see across these three is when we compare the local observations in green to two potential data sets, the Princeton Global Forcings and ERA 5, that for the moderate and early rainfall thresholds, the Princeton Global Forcings match the local observations relatively well, but once we use a much more strict criterion or a more moisture intensive criterion, then there starts to be greater divergence between the data sets. Similarly, we can look at the occurrence of break periods, and here we were testing with a period of 7 days and then detecting what fraction of the month subsequently continued to have a consistent 7 days without rainfall. And here we find that there's actually a substantial amount of disagreement among the data sets. There's very subjected to threshold effects at this point. And one other thing to mention at this point is this is just preliminary work, because what we're waiting to do is couple or join our analyses in this domain with outputs from particularly the Manchester agricultural team to identify, and the partners and the collaborators based in Ghana, to identify what the actual physical meaningful thresholds for some of these impacts or phenomena are, so that the metrics we're calculating have relevance in terms of local perception and local behavior of systems, and particularly crop yields in this zone. So the second key aspect of Newcastle's work on the FutureDAMS project is to synthesize data sets which can be used to drive the simulation of future conditions in various impact and framework models. And so in order to explain that, first I will provide some background on how global climate simulations are formulated, and particularly the emission scenarios that go into driving them. So in order to figure out or to calculate emissions scenarios, economists and social scientists collaborate with atmospheric physicists and climate modelers to define scenarios used in the simulations of future climate conditions. So these scenarios take into account global land use patterns, things including deforestation, conversion of land to agriculture, or fallowing of land, urbanization, and a range of other processes, and as well as technology-based economic levels of activity. So you may be familiar with the concept of carbon intensity, the amount of greenhouse gas emissions per unit of GDP. And those kind of aspects are considered to yield trajectories of potential greenhouse gas emissions over the coming decades through the end of this century. And there's a great deal of uncertainty in these processes, but there is good agreement that high emission scenarios would have different outcomes for both societies and ecosystems than lower emission scenarios. So the interdisciplinary work that is collaborated to derive these formulations decided to illustrate these patterns on two axes. One, in terms of socioeconomic challenges for adaptation. So how much resources were available to help societies cope with climate change? That's in the horizontal. And socioeconomic challenges for mitigation in terms of what the industrial patterns or economic patterns of activity were that would lead to greenhouse gas emissions. And so in the lower left quadrant, and kind of the idealized scenario, we idealized from a sustainability ecological standpoint, we have the low challenge of sustainability, SSP1. Logically, in the center of the graph, we have the middle of the road scenario where there is a mix of economic activity, so a variety of not either very low emissions nor very high emissions, and also a range of a moderate amount of economic resources available to help cope with the impacts of climate change. The lower right quadrant is perhaps not the most widely considered, but it is something that was identified in mapping out these ranges, where we could have a case where there's relatively low emissions output for a range of reasons, but also very low resources available for adapting to whatever level of climate change there is happening. And then the upper level of the graph is probably what is most often considered in terms of preparing societies for potentially large challenges. And so the upper left part of the graph is the traditional high emitting, high polluting scenario, but that supposes or assumes that those highly polluting activities would yield economic benefits, which would also then enable some technological capacity for adapting to or surviving climate change impacts. And then the upper right quadrant, SSP3, is potentially the worst case scenario, where there's still a high level of emissions, but there's also relatively limited resources available to cope with the impacts of climate change. And so these are these shared socioeconomic pathways scenarios are effectively could be described as narratives, trying to relate patterns of describable human activity, qualitatively describable patterns of human activity, to levels of pollution and levels of capacity for coping with climate change. These shared socioeconomic pathways are then translated into, based on specific expectations of emissions of greenhouse gases, to radiative impacts that are used in terms of what the actual greenhouse or global warming effect will be, and those are quantified by the atmospheric physicists and climate modelers in terms of a forcing in watts per square meter that would be happening at the end of this century. And so we have here in the right side of the figure, under previous scenarios, the green blocks relate to scenarios that were available or outputs that were produced during the previous generation of climate models, CMIP 5, which was produced for the preceding IPCC report, than the one that's being currently compiled. And we can see that essentially this new set of socioeconomic pathways matches or covers those scenarios but expands upon them. So everything with a white block, in theory, there is at least one modeling group around the world that is producing a scenario or running climate simulations that address this. But what we see is that the blue boxes are the areas where there's the most focus of modeling effort. So in the upper right hand corner we have SSP5, which had been the traditional worst case scenario. It relates to a radiative forcing of 8.5 watts per square meter, and so there's a substantial amount of work modeling model outputs that will be available for that. In the other somewhat worst case scenario, SSP3 at 7 watts per square meter, there are also a substantial number of scenarios being produced, and again for the middle of the road scenario, 4.5 watts per square meter, that is being reduced, as well as some of the best case scenarios, the 1.9 and 2.6 watts per square meter scenarios under SSP1, which would relate to satisfying various levels of the Paris of the goals related to the Paris Climate Accords. So these varying levels of emissions, greenhouse gas emissions represented by the various shared socioeconomic pathways, would logically or are projected logically to have varying outcomes in terms of global mean temperature. And so these are global values, and you can see solid lines being ensemble means and then shaded areas being ensemble ranges across climate modeling, clusters of climate models. That's at the left panel. On the right panel, we can see for the 30-year period from 2071 to 2100, the range and distribution of model ensemble members. And one of the interesting things to note is that because of the spread and uncertainty across the models that compose these ensembles for the various scenarios, that there is some overlap. So the low end of estimates, for instance, of SSP3 are within the upper end of estimates of SSP1 and so forth. So that's all work that's being done by global climate model institutes that Newcastle will be drawing upon their outputs. And so what Newcastle will be taking that available information and doing with it for FutureDAMS is, as I said at the beginning of the presentation, to produce synthesized portfolio of data sets which will be available to drive the impact and framework models. And so what we've done thus far is we produced a set of placeholder climate scenarios which were made quickly available for testing the modeling frameworks that are being developed, so to make sure that with the planned future climate model outputs. So to do this, we went through a multi-step process we assessed the spread in the preceding generation of climate models. We're still in the process of acquiring the newest CMIP 6 climate modeling outputs, but we assessed the spread of projections from CMIP 5. We identified models that were showing relatively moderate and severe precipitation and temperature changes. We looked at the models that were clustered in those areas, and then we identified a subset which had the best, most reasonable performance in simulating historical climate. And then we extracted an anomaly series over the geographic areas of the FutureDAMS case studies to guide resampling of the historical baseline climate dataset, which, as I've been alluding to, is the Princeton global forcings. And then we introduced that climate change signals from that anomaly series to perturb the resampled historical baseline series. And so this was done using a transient time series starting from the end of the historical Princeton global forcings dataset through the year 2100. And in the placeholder datasets, we chose to produce data for one example each of moderate and severe cases of both the 4.5 and 8.5 climate emissions radiative forcing scenarios, which relate to effectively the middle of the road in worst case scenarios on CMIP 5 and have, as I was showing, the equivalence under CMIP 6. And in producing these data sets, there's a wide range of climate variables which are required by the various sectoral modeling teams, and we're producing these on a quarter degree, which is roughly 25 kilometer grid at the equator. And the time step was produced as a 3-hourly time step because that matches with what is required for the hydrological simulations and is close to what is preferred by the energy infrastructure modeling teams. And so that was how the placeholder climate data sets were produced, and we will be implementing a number of refinements or improvements when we produce the final climate scenarios. First of all, we will be using outputs from the newest GCMs, i.e. from CMIP 6 rather than CMIP 5. We will perform more detailed evaluation of climate model performance for historical periods. We will refine analyses in the spread projections to inform our scenario selection, and then we will identify and synthesize mini ensembles to better account for internal climate variability or sequencing, stochastic variability, year-to-year variability, or sequences of years interdecadal variability within the scenarios to give an added degree of robustness to the impact and framework modeling efforts. So, how the work proceeded for the placeholder dataset production. These are looking at the left hand, we have the middle of the road RCP 4.5 emission scenario. On the right hand, we have the highly polluting or worst case 8.5 RCP 8.5 radiative forcing scenario, looking at annual mean changes for temperature and precipitation for 3 of our case study basins. Myanmar at the top, the Nile in the middle, and the Volta in the lower. 2040 is the left-hand set of columns, and 2071 is the right. And temperature is on the vertical axis, and degrees of temperature change in Kelvin, which is the same as degrees of temperature change in degrees Celsius, and then precipitation change as a multiplier of the historical mean value. So a 1.0 in precipitation is zero change, no change at all, and then values less than 1 indicate a drying in the annual precipitation, and values greater than 1 indicate an increase in projected annual precipitation. And so the arrows for the Volta panels indicate selected climate models that were chosen to represent the moderate and severe cases that went into the placeholder datasets. And so in selecting which exact model in clusters near to the arrowheads in the previous graph, we also looked at the representation of the annual cycle, and we can see that while many models have, several of the models within each of the ensembles. So on the left we have historical volta precipitation, on the right we have historical volta temperature, and this is similar to the graphs that I showed for evaluation of a given station. These graphs were produced by doing spatial averages across the Volta Basin using the Princeton Global Forcings as the baseline reference, SOTO 25, because the data came via Southampton, and then the individual models. And we can see many of the models have reasonable representation, some have relatively highly biased formations for both precipitation and temperature. So one of the underlying assumptions is that the models that represent the historical baseline correctly would hopefully be more reliable in their representation of future conditions, although there is a degree of hazard in that for the present period the models could be showing the right answer for the wrong reasons. In other words, they could be having two errors that balance each other out and thus give an appearance of accuracy, and in the future condition it might be that one of those elements no longer balances the other. So that is one of the motivations for taking in a broad ensemble of climate models in terms of simulations of future impacts. And so these are examples for the spatial mean across the Volta Basin at a monthly time step of projected future temperature. You can see in the black lines is the annual cycle of oscillation of temperature across the basin, and then in the orange lines are calculated annual means. And what we can see in these graphs, the top is the moderate version of RCP 4.5, the middle of the road, and then proceeding downward we have the severe version of the middle of the road emissions, and then we have the moderate version of the high emission scenario, and the bottom we have the severe version of the high emission scenarios. And what we can see a number of things from this graph. First of all, it takes a few decades going closer to 2050 before the temperature signal begins to, the annual temperature warming signal begins to substantially exceed the historical period. Secondly, we also see a substantial amount of overlap or similarity in magnitude of temperature change between the severe version of the 4.5 or middle of the road scenario and the moderate version of the worst case scenario, and that's an important element to bear in mind in terms of the range of uncertainty within these versus the distinction between the scenarios themselves. But what we do see is that under the 8.5 radiative forcing severe emissions scenario, or severe version of the high emission scenario, the temperature warming would be on the order of 5 degrees or more. The x-axis, the y-axis here is shown in Kelvin, which is differentiated from Celsius, of course, by 273 degrees. But the blue line represents the historical baseline, so that the difference between the blue line and the orange line can give you the idea of the change or increase in temperature. In contrast to precipitation, at least in the simulation or the generation of the placeholder data sets, there wasn't really a clear pattern in mean precipitation change amongst the models that were available in this ensemble, although one of the things we do see potentially indicated in the RCP 8.5 sequencing is that there is possibly some indication of subsequent dry years, particularly in the latter time periods of this remaining decades of this century. But overall, this also illustrates that the global warming or climate change will be most evident in the changes in mean temperature, whereas because of the highly variable nature of precipitation, it will appear quite chaotic, and specific mean changes may not be apparent within the noise of year-to-year variability. Thus, what might be while future precipitation is highly uncertain, increased drying of soils, increased evaporative demand from increased radiative inputs seems highly likely. So to wrap up this presentation, which has gone on for quite some time, the team here at Newcastle, we are endeavoring to provide scientific outputs to help other teams in the consortium avoid the garbage in pitfall, which frequently occurs in modeling work of various disciplines. Evaluations thus far, but which have been limited to the Volta Basin, showed the Princeton Global Forcings dataset to be the most credible basis for impact modeling analyses. Climate metrics analyses could yield valuable insights separate from modeling work, but the metrics would need to be coupled or designed in conjunction with basin-specific knowledge so that we can skillfully parameterize their definitions using physically relevant thresholds, particularly for phenomena such as monsoonal onset or break periods within a monsoon intra-seasonal variability. Owing to the broad uncertainty in both the actual pathway that global greenhouse emissions will take, as well as the scientific uncertainty regarding which algorithms best represent key climate processes, at present a broad envelope of potential climate conditions over the remainder of this century are possible. And taking this into account, the Newcastle team, in consultation with other teams across the consortium, both based in specific case study basins and well as sectoral modeling teams, will produce a portfolio of projected future climate data sets manageable in volume so that the impact framework modeling can efficiently assess the potential implications across this envelope of uncertainty. Thank you for your time. Unfortunately, obviously, we can't be present in person for your questions, but feel free to email me if you have any questions. Kind regards.